Hi, my name is William. In this video, I'll present joint work with Dean Duran and Puya Hatami about pseudorandom generators. Randomness is a valuable computational resource, but it's also an expensive resource, like time or space. All else being equal, an algorithm that uses fewer random bits is better than an algorithm that uses more random bits, just like a faster algorithm is better than a slower algorithm. A pseudorandom generator is a powerful tool for improving the randomness complexity of algorithms. A pseudorandom generator is a function that stretches a short s-bit truly random seed out to a long n-bit pseudorandom string. To make this precise, consider some function f, which represents whatever process is using these n bits. We say that g fools f if the expectation of f on the pseudorandom distribution is within plus or minus epsilon of the expectation of f on a truly random input. This parameter epsilon is called the error of the pseudorandom generator. We would like to design a single pseudorandom generator that simultaneously fools a whole class of functions f, defined by some model of computation or some complexity bound. And we want the seed length of the pseudorandom generator to be as small as possible. In most cases, the optimal seed length is log n over epsilon. For us complexity theorists, pseudorandom generators are closely connected to problems such as L versus BPL. It's conjectured that L equals BPL, meaning that randomness is not necessary for space-efficient computation. So, you can go ahead and throw all your coins in the trash can. The main approach to trying to prove L equals BPL is to design a pseudorandom generator that fools a model of computation called polynomial width read-once branching programs. For this application, we would like a pseudorandom generator with seed length O of log n. So far, that goal has not been achieved. To make progress, one could try to design pseudorandom generators for polynomial width read-once branching programs with shorter and shorter seed lengths, working down to a logarithmic seed. Unfortunately, by that metric, there hasn't been any progress in 30 years. At the opposite extreme, we can instead insist on seed length O of log n and try to design pseudorandom generators that fool more and more powerful models of computation, working up to fooling polynomial width read-once branching programs. That's what this work is all about. We focus on read-once depth-2 AC0 formulas with parity gates. So that is, we're considering depth-2 formulas with AND gates, OR gates, and parity gates. The gates have unbounded fan-in, and negations are allowed for free. And then the formula is read-once, which means every variable appears at most one time. So here's an example on the slide. As a special case, this class includes read-once CNFs and read-once DNFs. It also includes read-once polynomials over the field with two elements. In fact, this model is essentially equivalent to read-once polynomials. In the other direction, every read-once depth-2 AC0 formula with parity gates can be simulated by a width-4 read-once branching program under some variable order. There's a lot of prior work developing pseudorandom generators for read-once CNFs, read-once polynomials, and generalizations of those models. These are very well-studied models of computation. A recent line of work has provided near-optimal pseudorandom generators for read-once polynomials. And in fact, those generators also work for the slightly more general model that we're considering. However, almost all of these prior pseudorandom generators have seed lengths larger than log n. For read-once polynomials, there was no known prior pseudorandom generator with seed length O of log n. For read-once CNFs and DNFs, which is a slightly easier case, it was possible using prior work to achieve seed length log n, but only for constant error. Okay, here's what we achieve. We design a pseudorandom generator for read-once depth-2 AC0 with parity gates, including read-once CNFs and read-once polynomials, and our pseudorandom generator has seed length O of log n plus O tilde log 1 over epsilon. So notice that our pseudorandom generator maintains the optimal seed length of O of log n, even with near optimal error of 2 to the minus omega tilde log n. We design our pseudorandom generator using the framework of iterated restrictions. This framework was pioneered by Itai and Vigderson, and then more recently it was revived and developed by Gopelin, Mecca, Reingold, Trevisan, and Vidon. Here's the idea. Ultimately, we want to use a few truly random bits to sample a pseudorandom n-bit string. But let's take baby steps. We begin by sampling a pseudorandom restriction, which is a string over the three-symbol alphabet 0, 1, star. Intuitively, if some coordinate is star, that means the coordinate has not yet been assigned a value. To put it another way, we're pseudorandomly assigning values to a pseudorandomly chosen subset of the variables. Then, we'll sample more and more restrictions to assign values to more and more coordinates. In the last decade, there has been a lot of success using this framework to develop pseudorandom generators for many different models of computation. However, our work is the first time this framework has ever given a pseudorandom generator with seed length O of log n. That was really the initial motivation for this work. We wanted to see how far we could push this framework. Prior pseudorandom generators using this framework tend to have seed length polylog n, or at best O tilde log n, but we managed to go all the way to O of log n. In the rest of this video, I'll tell you a little bit about our construction and analysis. Let's start by just focusing on a single pseudorandom restriction. We'll think about iterating the process later. The construction of our pseudorandom restriction is very similar to prior work. The analysis is really where the action happens. Here's the construction. We use almost log n-wise independence to select the star positions. We set the star probability to a constant very close to 1, or in other words, we're selecting a tiny fraction of the coordinates to assign values to. To fill in those values, we use something called a small bias distribution, which means a distribution that fools parity functions. Small bias distributions are a standard tool for pseudorandomness problems. So using standard constructions, the total cost of our pseudorandom restriction is O of log n truly random bits, which we can afford. Here's the correctness guarantee. Let F be a read-once depth-2 AC0 formula with parity gates. Consider two thought experiments. In the first experiment, we sample our pseudorandom restriction, x, and we use it to restrict the function f, and then we set the remaining living variables using truly random bits, u. In the second experiment, we just plug in a truly random input to f. What we prove is that the expectation of f is essentially the same in these two experiments. It's the same to within error 2 to the minus log n over log n, which is near optimal. To put it another way, the pseudorandom restriction x approximately preserves the expectation of f. Unfortunately, the proof of this theorem is pretty complicated. For simplicity, assume f is a read-once polynomial, right? Or in other words, a parity of ands of variables. Like I said earlier, this assumption is essentially without loss of generality. The proof of the theorem involves a lot of casework, where we do one thing if there are a ton of low-degree terms, and we do a different thing if there aren't so many low-degree terms, etc. For this presentation, I'll just focus on the parts of the proof that I think are the most interesting. Let Z be a bit string indicating the star positions in our pseudorandom restriction. So technically Z is a random variable, but let's fix a value for Z, and later I'll just implicitly assume that Z has certain properties we need. Once Z is fixed, for any function f, we can define something called the bias function, tilde f. So to be clear, the bias function is not directly related to small bias distributions, even though they both use the word bias. Here's the definition of the bias function. On an input x, the bias function randomizes some of the bits of x, the bits where z indicates a star. Then the bias function plugs that distribution into f and outputs the expectation. So it's a real-valued function. In other words, we use x and z to define a restriction, and then the bias function outputs the expectation of the restriction of f. Now remember, in our actual restriction construction, we choose the assigned bits using a small bias distribution. So to show that our restriction is good, we need to show that small bias distributions fool the bias function tilde f. Let's manipulate the expressions a little to facilitate the analysis. First, let's translate the outputs from 0, 1 to plus or minus 1. Okay, so remember f is a parity of all its terms, and so when we make this translation, the parity becomes a product. Now f is the product of these m terms, each of which is a conjunction of variables. Next, let's define a function fi bar. Fi bar is a normalized version of the bias function of fi. Okay, it's the bias function of fi divided by the expectation of fi minus 1. That way, if we rearrange, the bias function of the ith term can be expressed as the expectation of that ith term times 1 plus fi bar. So fi bar sort of captures the deviation from expectation of this ith bias function. All right, so altogether, here's the formula for the bias function of f. The bias function of f is the product of the bias functions of all the terms. So it's the expectation of f times the product over I of 1 plus fi bar. To analyze this formula for the bias function, we use an approach based on symmetric polynomials. This approach was introduced by Gopelin, Mecca, Reingold, Trevisan, and Vadan, and it was subsequently used in a couple other papers. The approach works best if f is a homogeneous polynomial. So let's say it's a polynomial of degree d. Recall that the kth elementary symmetric polynomial is denoted sk, and it's defined to be the sum over all k-sets, I, of the product of the variables with indices in I. We can use these elementary symmetric polynomials to expand the product in the expression, the formula for the bias function. Right, the bias function is given by now the expectation of f plus this error term. The error term involves the sum of the elementary symmetric polynomials applied to all the fi bar functions. And remember, fi bar captures the deviation of the ith term's bias function from its expectation. To prove our theorem, we should show that this error term has a near zero expectation under the small bias distribution. Here's how prior work has attacked this problem. We split the sum up at this cutoff point, k0, which is roughly log n over d. Remember that d is the degree of the polynomial. For the early error terms, when k is less than k0, we use some straightforward Fourier analysis to argue that the small bias distribution fools these terms. For this to make sense, we're going to assume that the number of terms is at most exponential in the degree. That way, the total number of monomials inside one of these early sk terms, m choose k, is bounded by 3 to the d times k0. By our choice of k0, this is a polynomial in n, so our small bias distribution can take care of it. Next, consider the middle error terms, i.e. the case that k is approximately equal to k0. Not only are these terms near zero in expectation, we also show that they are near zero with high probability. At an intuitive level, the reason is that the bias function involves averaging over a bunch of random inputs, which smooths everything out and reduces all the variances. Quantitatively, the bound we get this way is exponentially small in this quantity, k times d. Finally, consider the late error terms, when k is larger than k0. For these terms, we use a tail bound for symmetric polynomials. There are these cool theorems that say, if two sk's in a row are near zero, then all the subsequent sk's are also near zero. Since sk0 and sk0 plus 1 are both near zero with high probability, this takes care of all the late error terms. I want to draw your attention to the value of this cutoff parameter k0. We needed to make sure it's not too big so that the Fourier L1 bound works out. But we also needed to make sure it's not too small so that the middle terms are sufficiently smoothed. It's like a Goldilocks condition. We need to choose k0 just right. For both the upper and the lower bound, what we need is that this quantity d times k0 is approximately log n. A difficulty with this approach is that the polynomial f is not necessarily homogeneous. right? It might have some high degree terms and some low degree terms. We can partition the terms into buckets based on their degree. So all the terms in bucket J have roughly the same degree, 1.1 to the J. That way, within each bucket, the analysis on the previous slide makes sense. We can choose the cutoff point, k0, to be log n over the degree, showing that the small bias distribution fools the bias function of that bucket. But now we need to somehow combine these results to fool the bias function of the whole function altogether. Here's how previous works have handled this issue. There's a generic XOR lemma for small bias distributions. It says, suppose we have any q functions on disjoint variables, and assume that each one is fooled by small bias distributions. Then their product is also fooled by small bias distributions. In our case, this product makes sense because our polynomial f is the product of all the buckets. The unfortunate thing about this approach is that there is an unavoidable loss in parameters. The effect is that we have to pay a factor of q in terms of the seed length. For us, q is the number of buckets, which ends up being log n. That's a pretty small factor, but we can't afford it. Remember, we want our seed length to be O of log n. So we have to do something new to beat this XOR lemma approach. Let me try to give some intuition. Let's return to this formula for the error in terms of elementary symmetric polynomials. And let's return to the homogeneous case when things work well. Suppose the degree of f is d, so we can set k0 to be log n over d like we wanted. And let's consider the middle error terms when k is approximately equal to k0. By the definition of sk, each monomial of sk involves k of these fi bar functions. Right, here's an example when k equals 3 and m equals 4. But that's kind of the wrong way to think about it. Each fi bar is itself some function of the underlying input variables, x1 up to xn. Since f is a degree d polynomial, the definition of fi bar involves d of these underlying input variables. What that means is that altogether, each monomial of sk involves k times d of the underlying input variables. There's that quantity k times d again. Intuitively, this is the reason that it's a good idea to set k0 to be log n over d. That choice of k0 ensures that each monomial of sk involves roughly log n of the underlying input variables. I hope that helps to clarify why things go wrong when f is not homogeneous. If f is not homogeneous, then for each fixed k, some monomials of sk involve more input variables than other monomials of sk. Those considerations suggest that perhaps elementary symmetric polynomials are not quite the right tool for the job. Let's revisit the bias function. Remember, we have this formula. The bias function is equal to the expectation of f times the product over I of 1 plus fi bar. We can expand that product into this giant sum of length 2 to the m, right? We just sum over all index sets I. Basically, the point of the symmetric polynomials was to help us with bookkeeping. They organize all these 2 to the m summands, helping us to keep track of the number of fi bars that participate in each summand. But we would like to keep track of the number of underlying input variables, the xi's, that participate in each summand. So let's reorganize these summands using a new family of polynomials. That's why we introduce a new family of polynomials in our paper. We call these polynomials subset-wise symmetric polynomials. Here's the definition. Fix some partition of the indices 1 through m into buckets, b1 up to bq. The old elementary symmetric polynomials were parameterized by a number, k. Our new polynomials are parameterized by a whole vector, k, a list of q non-negative integers. On an input y, we sum over all index sets that pick out k sub j indices from bucket j. And then for each such index set, we do the product of those coordinates in y. That's the definition. So, to compare, in the old elementary symmetric polynomials, the parameter k specifies the number of yi's that participate in each monomial. But in these new subset-wise symmetric polynomials, the vector k specifies the number of yi's from each bucket that participate in each monomial. So we're keeping track of more data. Okay, so that's the definition of the new polynomials. Now let's return to proving that our restriction preserves the expectation of our function f. Remember, bucket j consists of terms of degree roughly 1.1 to the j. For a vector k, let's define the norm of k to be the weighted sum of its coordinates, where the jth coordinate is weighted by 1.1 to the j. Remember the meaning of this vector k. The coordinate k sub j counts the number of fi bars from bucket j that participate in each monomial of sk. So the way we've set things up, this norm counts the number of underlying input variables that participate in each monomial of sk. Alright, so now let's return to this formula for the bias function of f. Remember, the bias function of f is given by the expectation of f times the product over I of 1 plus fi bar. Now let's expand that sum using our new subset-wise symmetric polynomials. So now we have the expectation of f times the sum over all k vectors of s sub k applied to f1 bar up to fm bar. This way, we can split the sum into the early terms and the late terms based on the norm of k as defined on the previous slide. The cutoff point is when this norm is roughly log n. That way, the early terms are the ones where each monomial only involves a few of the underlying input variables, and the late terms are the ones where each monomial involves a lot of input variables. To adapt the previous analysis from here, in the paper we proved tail bounds for these subset-wise symmetric polynomials that are similar to the known tail bounds for elementary symmetric polynomials. So in some sense we are handling all the buckets simultaneously and we no longer need the XOR lemma. I left out quite a lot of details, but I hope that gives you some sense of how we are able to prove that our pseudorandom restriction preserves the expectation of f to within near optimal error. Let's move on at this point to the problem of constructing a full pseudorandom generator. Remember, so far I've only described a way to pseudorandomly assign values to a tiny fraction of the inputs. Our restriction does preserve the expectation of the formula to within near optimal error, but it also costs us O of log n truly random bits. That's our entire budget of randomness right there. It might seem hopeless to try to iterate the process to get a full pseudorandom generator. Here's what saves us. Suppose f only reads n prime variables where n prime is smaller than n. Then, by slightly modifying our restriction, we can make it so it only costs O of log n prime truly random bits, instead of O of log n truly random bits. That allows us to pay less and less for each restriction as we go. Let me explain what I mean. For simplicity, assume once again that f is homogeneous of degree d, which is roughly log n. Let p be the fraction of variables that our restriction keeps alive, the star probability, so p is a constant very close to 1. After we do I restrictions, each term should have degree roughly p to the I times d. For simplicity, let's assume that this works out exactly, so the polynomial is still homogeneous, it's just now the degree is p to the I times d. Assume also that the number of terms is always at most exponential in the degree, just for the sake of discussion. Okay, so after I restrictions, the number of relevant variables, n prime, is the number of terms times the degree. So it's roughly exponential in p to the I times d. Our next restriction costs O of log n prime truly random bits, which is roughly p to the I times d. Now let's sum up the costs. If we do t restrictions, then the sum of all these costs is this decreasing geometric series. It converges to O of log n. So we can iteratively apply our pseudorandom restrictions as many times as we want, because no matter how many times we do it, the total cost is bounded by O of log n truly random bits. That's within our budget. Something I swept under the rug there a little bit, though, is that the error of our restriction is increasing with each iteration. It's getting worse and worse. For that reason, we only iterate our restriction log n times. After that, there aren't too many remaining living variables. This allows us to finish the job using a prior pseudorandom generator by Lee. This prior pseudorandom generator is only near optimal, but since we have so few variables left, it only uses O of log n truly random bits. Hopefully that gives you some idea of how our pseudorandom generator works. It's too bad that our pseudorandom generator doesn't quite have an optimal seed length in terms of epsilon. It would be great to design a pseudorandom generator with optimal seed length O of log n over epsilon, even if it's just for the special case of read once CNFs. Anyway, thanks for watching this video, and please don't hesitate to contact us if you have any questions or comments.